Right, I'm going to talk about Muirhead's inequality. It's very powerful. It's very general. You can extract all sorts of other inequalities as special cases. Um, it's also somewhat controversial. Well, the mathematics is what it is, but it's controversial as far as Olympiad questions go because some people say it's wonderful, you should use it all the time. It's a little known technique and you can quite often find a nice clever shortcut for stuff, for proving things. And other people say, well, you shouldn't really use it because you can always reproduce Muirhead's theorem with other inequalities. Well, I don't know, but I'm going to teach it anyway. Even to state Muirhead's inequality is quite difficult, so I'm going to split this into 4 or 5, haven't quite decided yet, screencasts. So first of all, I'm going to talk about majorization. We need various majorization, which is quite a nice little concept. If I have two sequences, x1 up to xn and y1 up to yn, non-negative, and I'm just going to consider integers for the moment. These are just integers. Then if, well, no, let's state it exactly. We can write x as the entire sequence to xn, and y with this kind of underline equals y1 through yn. Then we write that x majorizes y, that's the whole sequence, and we say that x majorizes y if the following. Well, first of all, the totals have to match of yi, so the totals match. But we've also got the following system of inequalities as well. We know that x1 has got to be greater than or equal to y1, x1 plus x2 greater than or equal to y1 plus y2, x1 plus x2 plus x3 greater than or equal to y1 plus y2 plus y3, and so on. And in general, sigma from I equals 1 to r of xi has got to be greater than or equal to sigma from I equals 1 to r of yi. However, the total of the whole sequence has to match. And if that's the case, we say that x, the sequence, majorizes y. It's kind of written in this peculiar, it's not a greater than, it's kind of a curved greater than symbol. Okay, x majorizes y. Let's just have some examples of that. Let's just have some examples. So if x equals, let's say, 3, 0, 0 and y equals 1, 1, 1, then x certainly majorizes y. Well, because the sum of x equals 3 and the sum of y equals 3, so the sum of the whole sequence matches, but also the partial sums are in the right order. So 3 is greater than 1. The next one is 3 plus 0, which is 3 plays 2. 3 is greater than 1. 3 plus 0 greater than or equal to 1 plus 1. And of course, 3 plus 0 is greater than or equal to 1 plus 1 plus 1 plus 1 plus 1. So that's a nice little example. Let me give you another one. 4, 2, 1, that's x, and then y equals total 7, doesn't it? So it could equal 3 and then 2 and then 2. That's right, isn't it? Because they both total 7, and we know that 4 is greater than 3. 4 plus 2 is greater than or equal to 3 plus 2, so the first 2 of x is bigger than the first 2 of y. And 4 plus 2 plus 1 greater than or equal to 3 plus 2 plus 2. So that majorizes that. Okay, I'm going to stop there. That's majorization, and we're going to need it in subsequent screencasts, so I'm going to stop there.